Hello everyone, I'm Youjie, a PhD student from UIUC. In this talk, we propose a new computing paradigm and use it for training large DNN models on commodity servers. This work was started as part of an MSR internship with Amar and was in collaboration with Derek and Professor Kim. Over the years, the DNN model size are growing exponentially and continue to solve more complex problems. Back in the 90s, a tiny LeNet can only classify handwritten digits. Now, a GPT-3 with billions of weight can already write a realistic articles of that nature. As the model size grows, they also become harder to train. Especially, they consume huge amount of memory. Training the GPT-2 of 1.5 billion weight needs 128 gigabytes of memory, and the weights are only a fraction of the total memory usage. Now, training a large model is so resource demanding such that only the elites, the big companies who own a data center of GPUs can stay out in the game, such as using thousands of GPUs to train a GPT-3. But most researchers in the mass might only have limited resources, like a single servers with several GPUs. And they are being forced out of the game of playing large models. In this work, we explore how to radically expand the accessibility of training massive models on commodity servers. One of the major challenges of training large models is a memory footprint far exceeds the memory capacity of accelerator. For example, training GPT-2 requires an order of magnitude more memory than the capacity of a V100. The promising solution to this challenge is the GPU memory virtualization, which uses large CPU memory to back the small GPU and swap data structures between CPU and GPU memory. Prior works have already shown this technique allows single GPU to train large models. However, it comes with a price of excessive swapping overhead. For example, a model is going to compute several data batches in the timeline, and the GPU memory is virtualized, can hold one layer at a time. At the first data batch, the GPU needs to swap in the necessary model state to compute and then swap out for saving state changes. When the second data batch comes, the GPU needs to do this swap in, swap out again. This repeated swapping gives excessive overhead. Even worse is that we can have swap bottleneck, because in practice, training large models is always done by multiple GPUs for parallel training. And all these GPUs can swap concurrently and swap to nowhere but to the CPU memory through a PCI tree. And then the root PCI link easily becomes bottleneck, as it's often oversubscribed by 48 GPUs. Another promising solution is a model or pipeline parallel training. They partition a large model into smaller parts, such that each part requires much less memory footprint and potentially fit to each GPU memory. This is great for models that can fit collective memory capacity of all the GPUs. But sadly, on commodity servers, even with all the accelerator combined, their collective memory capacity can still not meet the memory footprint. This is because either the model size or data size is too large, or GPU is lower end, or we don't have enough GPUs, which are the common cases in commodity servers. So how to train large models on commodity servers, especially training them with great efficiency? They are still open questions. It is tempting to think about how to combine these techniques, such as pipeline training with each memory being virtualized. Unfortunately, it's still inefficient, because we can have unbalanced swap loads across GPUs. And the pipeline training naturally requires synchronization across GPUs. As a result, the heavy swapping GPU can easily become the system bottleneck. These inefficiencies are actually hard to solve, because they are caused by the fundamental limitations in today's ML frameworks. First, the scheduling is just too coarse-grained. For example, as shown earlier, the PyTorch schedules the entire model to compute the first data batch before switching to the second. Second, the binding to the devices are just too early. Even in the user script, we have already bound the first part of the model to the first GPU and second part to the second GPU. As a result, we can have better flexibility and resource utilization, which makes the swap inefficient. In this way, we propose a new computing paradigm called harmony, for training more with less. The key ideas are three. First, we decompose everything, no matter data, model, operations, into small tasks. Then we schedule those tasks at a fine granularity. With the fine granularity task, we late bind them, bind the compute, bind the swaps onto the given hardware. The goal is to maximize the system efficiency for training large models. This is a high-level overview of Harmony. The user only provides a data batch size and the model code to the Harmony. It then decomposes them into a fine-grained task and with late binding onto the given GPUs and interconnects. When we design Harmony, there are four guiding principles. First, always minimize memory swaps, which can be the major overhead. For example, we can group tasks in the timeline such that they can reuse the shared state that are already in the memory. Second, we can schedule tasks just in time. For example, we can schedule the task as soon as its input becomes ready, before waiting its input getting swapped out. Third, instead of putting all the swap to CPU, we should swap over the fast peer-to-peer links. Lastly, balance the compute and the swap load by packing multiple tasks or different tasks together. To illustrate better, let's look at this simple example of training 4-layer DNN onto GPUs. First, suppose we have all tasks decomposed already, and there are 3 types of tasks: forward, backward, update. And each task contains 1 layer and 1 microbatch. Then the Harmony will group appropriate tasks, move the swap to peer-to-peer, and just-in-time schedule them. The scheduled task can then be unrolled in timeline like this. As we can see on the first GPU, the first 2 tasks are grouped together such that they can reuse the shared layer 1 state in the memory by computing across 2 microbatches. This avoids repeated swaps. On the second GPU, the grouping are similar but with different layers, so on and so forth to group all the forward and backward tasks. Then the output of first layer are always peer-to-peer transfer to the second layer instead of swapping to the CPUs. Also, after backward task, the update task happens just in time, without waiting for the layer state being swapped out. So this task forms a virtualized pipeline running across 2 GPUs without capacity constraints. Lastly, the compute swaps peer-to-peer transfer running beneath the hood are handled by the Harmony runtime. We have more details of Harmony in the paper, such as how to view multiple accelerators as a single one, how to virtualize different parallel training, policy evaluations, multiple machine training, as well as trade-offs and the feasibility for the end-to-end training. Have a look if interested. To sum up, we propose a new solution of training large models for the mass. We identify the major challenges, study existing techniques, and understand their inefficiencies and underlying causes. Lastly, we advocate rethinking how ML framework, schedule compute, move data, really make it happen for efficiently training large models in commodity servers. We hope our work brings inspirations in this new research direction. Thank you.